Okay, 2 dots on a screen. How far apart are they? Easy. You measure the straight line between them, and you read off a number. That's the distance you learned as a little kid, and on a flat sheet of paper it works perfectly. But let me ask you a stranger question. How far apart are 2 songs? How far apart are 2 words? Or 2 towns, when the only way between them is a winding road? You can't lay a ruler across a song, and yet somehow we still feel that some songs sit close together and others sit far apart. So maybe distance was never really about the ruler. Maybe it's about a handful of rules the ruler just happens to obey. Let's find those rules after the break. Welcome back. We're going to throw away almost everything and keep only what we truly need. 2 things. That's all. The first is a collection of objects. We'll call each object a point, and we'll call the whole collection M. And these points do not have to be numbers. They can be towns, they can be songs, they can be little functions or shapes, or anything you can dream up. The second thing is a single rule. A rule that takes any 2 of those points and hands you back exactly 1 number, the distance between them. Mathematicians have a name for that rule. They call it the metric, and they write it with the letter D. So D of x and y is just a fancy way of saying the distance from point X to point Y. And that is the whole idea. A set of points and 1 distance rule. Bundle those 2 together, and you have what we call a metric space. But there's a catch. We can't let D be any old rule we feel like. If a rule is going to earn the proud name distance, it has to keep 4 promises. Just 4. Here's the first. The distance from any point to itself is 0. In plain words, you are never any distance away from yourself. You're already there. Obvious, sure, but in mathematics we say the obvious things out loud. Here's the second. If 2 points are genuinely different, the distance between them is greater than 0. So different things are always at least a little bit apart. Now picture breaking this promise. 2 separate points could sit 0 apart, as if they were secretly the very same point. The whole idea would fall over. So we don't allow it. And quietly, those first 2 promises together hand us something nice. Distance can never be a negative number. You simply cannot be less than nothing apart. Here's the third. The distance from here to there is exactly the same as the distance from there to here. The walk to your friend's house is the same length as your friend's walk back to yours. Break this one, and the trip out and the trip home could disagree. And how far apart would stop making any sense. And here's the fourth, the famous one. To get from a first point to a second, taking a detour through some third point is never shorter than going straight. Picture walking to a tree, and then from the tree to a swing. That 2-part journey can tie the straight walk to the swing, but it can never beat it. A shortcut is never longer than a detour. In symbols, d of x to y is at most d of x to z plus d of z to y. We call it the triangle inequality. And break it? Then a detour could somehow come out shorter than the straight line, and the word distance would mean nothing at all. 4 promises. That's the complete contract. Keep all 4, and your rule officially becomes a metric. And the set it lives on officially becomes a metric space. Nothing more is required. Now, our oldest friend, plain straight line distance on a flat plane, keeps all 4 promises without breaking a sweat. We call it the Euclidean metric, and it's the distance you've used every single day of your life. But here's the fun part. Now that we know the 4 rules of the game, we can go looking for players we've never met. Imagine a city built as a perfect grid of square blocks. You're standing on one street corner, and you want to reach another. You can't fly diagonally through the buildings. You walk along the streets, turning at the corners. So your real distance is this. Count the blocks you go sideways. Count the blocks you go up. Add them together. Does this rule keep the 4 promises? Walk it through in your head, and yes, every one of them holds. So it's a perfectly real distance. People call it the taxicab distance. Now let me show you the thing that genuinely stopped me the first time I met it. Pick a center point and gather up every single point that sits within distance 1 of it. That collection has a name. We call it a ball. And a ball, by the way, is always wide open, with no skin on its surface. We'll come back to that. On the flat plane, with ordinary straight line distance, the ball is exactly what your gut expects. A perfectly round disc. But in the taxicab city, the ball is not round. Not even close.
Every point 1 taxi block away traces out a diamond. Square balanced on its corner. Same word. Ball. Completely different shape. And the only thing we changed was the rule for measuring distance. Let's change it one more time. Now let the distance be your single largest step. The bigger of how far you went sideways and how far you went up. Just the larger one. Under this rule, the ball turns into a square sitting flat on the ground, its sides lined up neatly with the directions. So a ball can be round, or a diamond, or a flat square. 3 shapes, 3 worlds, 1 single idea. Or step off the flat ground entirely and stand on the surface of a globe. Up here, the distance between 2 points is the length of the shortest curve that hugs the surface between them. Straight lines don't even exist on a sphere, but distance still does. And it still keeps all 4 promises. And now, the strangest world of them all. Take any collection of points you like and declare this rule. The distance from a point to itself is 0, and the distance between any 2 different points is exactly 1. That's the whole rule. Everything that isn't you sits 1 single step away. Every other point, the same distance, no matter what. It looks far too simple to be allowed, but check the 4 promises, and it keeps every one. It even has a name, the discrete metric. And one more quiet idea before we start building. Take any metric space, reach in and grab a piece of it. That piece is automatically a metric space all on its own, using the very same distance rule it inherited. The fractions, sitting inside the full number line, are exactly this: a smaller world living inside a bigger one, sharing one rule for distance. Hold on to that. It's going to surprise us later. So why did we shrink distance down to 4 bare lines? Here's the payoff. Almost every deep idea about shape and nearness and holes and edges can be rebuilt out of one single thing: distance, and nothing else. So let's rebuild them. Right here, in this wider world, where a distance might be a diamond or a single step. We start with the ball again, the set of all points closer than some chosen radius to a center. That little ball is our building block. Now drop a point down somewhere inside a set and ask one simple question. Does this point have room to breathe? If you can draw a tiny ball around it, however small, that stays completely inside the set, then yes, it has breathing room. We call such a point an interior point. Collect all the interior points of a set together, and you get the interior of the set. And any set roomy enough to hold a little ball around a point is called a neighborhood of that point. Now, if every last point of a set is an interior point, every one with room to breathe, the whole set earns a special name. We call it open. An open set is all elbow room and no skin. Stand anywhere inside it, and in every direction there's a cushion before you reach the edge. The edge itself never belongs to the set. A closed set is the other kind. The plain definition is simple. A set is closed when everything outside it is open. And that works out to a lovely picture. A closed set is one that holds on to its entire edge. Nothing along the boundary is missing. Now let's play with these two, because they behave in ways that catch people off guard. Take any number of open sets, even infinitely many, and pour them all together into one big union. The result is always open. Roominess survives being combined. That always works. But overlap them instead, and things get delicate. The overlap of finitely many open sets is still open, but the overlap of infinitely many open sets can quietly stop being open. Here, watch. Take the open interval from -1 to 1, then from -1/2 to 1/2, then -1/3 to 1/3. Shrink and shrink forever. Each one is wide open, but the points shared by every last one of them? Just a single point. 0, all alone. And a lone point has no breathing room at all. It is not open. So infinitely many open sets, overlapped, collapsed into something that isn't open. That's exactly why we have to say finitely many. Closed sets do the mirror image. Overlap as many as you like, and the result stays closed. But only finitely many can be safely unioned. And here's a fact that quietly breaks the word opposite. Open and closed are not opposites. In any metric space at all, two sets are always both open and closed at the same time. The empty set, holding nothing, and the whole space itself. And in that strange, discrete world, where every point sits one step from every other, it gets wilder. Every single subset is open, and therefore every single subset is closed. all of them, both at once. Now here is something genuinely slippery. Whether a set is open depends on the world it lives in. Take the segment from 0 to 1 and make that segment your entire universe. Outside of it, nothing exists. Now stand at the very left end, the point 0. On the full number line, 0 sits right on a boundary. Take one step left and you tumble out of the segment. No breathing room, not an interior point. But if the segment is your whole world, there is no left of 0. There is nothing out there to fall into. So a little stretch starting right at 0 now counts as open, inside that world, even though it could never be open on the full line. The same exact points, opposite verdicts. Because open only ever asks about the world you are standing in. And there's a clean way to say it. A set counts as open inside a smaller world exactly when it's the overlap of some open set from the bigger world with that smaller world. The big world's openness, trimmed down to fit. All right, now let's look hard at the edge of a set, because the edge has a rich life of its own. Take a point anywhere and ask whether you can ever shake a set off. If every ball around that point, no matter how tiny, still holds at least one point of the set, then the point is stuck to it. We say the point is adherent to the set. A point of the set is adherent to it for free, of course. But here's the interesting part. A point can be adherent to a set without being a member of it at all, as long as the set keeps crowding right up against it from outside. We are about to see exactly that. Now turn up the strength. A point is an accumulation point if every tiny ball around it holds a point of the set other than the point itself. The set genuinely crowds in. And accumulation points carry a hidden punch. If a point is an accumulation point, then every ball around it doesn't just hold one other point of the set. It holds infinitely many. Picture the numbers 1/2, 1/3, 1/4, 1/5, marching on forever towards 0. 0 is an accumulation point of that little parade. Every window around 0, however narrow, catches infinitely many of them. And notice, 0 itself isn't even a member of the parade. There it is, adherent, crowded against, and not a member. Now picture the whole numbers. 1, 2, 3, 4. Spread out, each one alone, never bunching up. They have no accumulation points at all. Every one of them is what we call an isolated point, a member of the set with its own private elbow room. And then the fractions. Pick any number you like on the line, any one at all. Fractions crowd in on it from every side, as close as you please. Every single number on the line is an accumulation point of the fractions. That fact is about to matter. Gather a set together with every point it crowds up against, and you get its closure. The set, plus all of its accumulation points. And now we can finally say closed in the cleanest way of all. A set is closed exactly when it already contains every point it crowds against, when it equals its own closure. Nothing leaks out, and the set owns its whole edge. Now we reach the deepest idea in the whole chapter, compactness. And I want you to really see it. Imagine trying to cover a set with open sets. Toss them down like overlapping patches of cloth, as many as you need, until not one point of the set is left showing. That whole pile of patches is called an open covering. A set is compact if this is always true. No matter how someone covers it, no matter how many millions of patches they throw down, you can always step back, point to a finite handful of them, and say, these few already cover the entire thing. An endless cover and a finite handful is always enough. That is compactness. Let me show you a set that fails this. The open interval from 0 to 1. The numbers strictly between, not touching the ends. Cover it like this. The piece from 1/2 up to 1, the piece from 1/3 up to 1, from 1/4 up to 1, on and on. Each piece is open. Together they cover every point between 0 and 1. But now try to keep only finitely many of them. Finitely many always stop at some shortest piece, leaving a thin sliver near 0 completely uncovered. No finite handful ever finishes the job. So the open interval is not compact. The open end is the leak. And a set is bounded, simply, if the whole thing fits inside one single ball. It doesn't run off to infinity. Now, compact sets are wonderfully well behaved. A compact set is always both closed and bounded, and it has a beautiful trapping property. No infinite crowd inside a compact set can ever escape. Drop infinitely many of its points anywhere inside, and they are forced to pile up on a point that is still inside the set. Now, back in ordinary flat space, there's a famous and comforting shortcut. In ordinary space, closed and bounded means compact. Full stop. The two are the very same thing. That result is one of the cornerstones of the whole subject, and it carries a name: the Heine-Borel theorem. But that shortcut leaned on special features of ordinary flat space. Pull those features away, walk out into a stranger metric space, and the shortcut cracks straight down the middle. Let me show you the crack. Imagine your entire universe is the fractions. Only fractions. The irrational numbers, the ones whose decimals run on forever without ever repeating, simply do not exist in this world. Now fence off the fractions caught between two irrational posts. That fenced set is bounded clearly. And inside this world made only of fractions, it turns out to be closed. And yet, it is not compact. Here is exactly why. You can line up fractions inside the fence, marching closer and closer to one of those irrational numbers, getting nearer with every step. But that irrational number, their destination, does not exist in a world made only of fractions. There is a hole, right where their meeting point should be. So this infinite crowd of fractions is sneaking up on a point that was erased from the universe. They escape, straight through the gap. Closed, bounded, and still not compact. The comfortable shortcut is gone. So what survives out here in every metric space, no matter how strange? This, the real heart of compactness. A set is compact exactly when no infinite crowd can ever sneak out through a gap. Every infinite piece of it must pile up on a point that is genuinely there, inside the set. That, and not closed and bounded, is the idea that travels everywhere. And one clean gift comes along with it. Carve a closed piece out of a compact world, and that piece is compact too. One last idea, and it wraps the edge up beautifully. The boundary. Stand on a single point and look at every tiny ball around you. If every one of those balls straddles the fence, catching at least one point of the set, and at least one point of the outside, then you are a boundary point. You are sitting right on the dividing line. The boundary of a set is just all of those fence-sitting points gathered together. And the boundary is always a closed set. It owns its whole edge. There is a tidy way to describe it. The boundary is what the closure of the set and the closure of everything outside it have in common. The two closures, exactly where they meet. For a round ball, the boundary is just the thin shell wrapped around it, the sphere right at its surface. No surprise there. But here's a final shock, and it ties our whole journey together. Go back to the fractions, sitting once more inside the full number line. What is their boundary? Every interval, however unimaginably tiny, holds both fractions and irrationals, packed together with no gaps between them. So every single point on the line straddles the fence. Every number on it, without exception, is a boundary point of the fractions. The boundary of the fractions is the entire number line. The fractions have no roomy inside at all. They are pure edge. Every last point of them sits on the boundary. So look at everything that distance gave us once we trimmed it down to 4 honest promises. Open sets and closed sets. Crowding points and closures. Compactness and the cozy shortcut that quietly fails the moment you leave home. And boundaries that can swallow a whole line. All of it, every piece, built on one humble number. How far apart? And in the next chapter, we finally set the whole thing into motion. What does it even mean for a function to be continuous when close might be a diamond, or a globe, or a single solitary step? That's where we're going next.